Now I want to explain three important articles: TransferNet, subgraph retrieval enhanced model, and another article. So this article from Tsinghua University, the best university in China, is an interpretable reasoning network for multi-relation. And I will explain it in just two slides, this slide and this slide, because it's very easy and very interesting. So the idea is that they have one more thing. They have a state. So they have question at each step. They pay attention to different words in a question. For example, daughter here and how old here. So at each step, at each hop, we pay attention to different parts of the question. And also it also encodes the states. So these are the states. And these are the answer. Of course, we don't need this one, but for interpretability issues, we also learn that as well. So we can also answer different questions as well. But in our QA, question answering training data point, so the goal of our training is just to answer this, but we can also say something about intermediate queries, let's say. So the question say that it's just an average of some word to vec, and then you change your queries. So at each step, as I said, we pay attention to different words of the question, and then we obtain which relations maximizes that likelihood that corresponds to this loss. But here the loss is just using this cross entropy, and same for relation and same for these answers. And there are three maps that I didn't like because there are so many maps. First, you go from relation to state, because we should be in the same semantic space. So we go from a relation to state. Here we go from a relation to question, and here we go from state to entity. So I don't want an algorithm to be very complex, because our mind is not complex. So we should try to reduce the complexity of our models, because we can solve it simpler, much simpler. And so we have loss for relation, and we have loss for answer. So this lambda determines the trade-off between relation and answer. Of course, answer is more important. Relation could be used for example, interpretability or transparency in the intermediate steps. So when dealing with conjunctive questions, this article is not good, because it's just adding these two distributions. This is good, but here we should rewrite the question again for each of these words, such as forward or BD or any word. But let me explain TransferNet, which is really important article, and again from this great university in China, the best university in China. And so relations here are either in label form or in text form. Text, it is economical, because if it is in label form, it's very expensive. You need those information extraction steps that I will explain next lecture. And so because converting a text to knowledge graph, people say it is expensive, but nowadays it is becoming less and less expensive. But still it takes time. So it's an intermediate step. So you could use it for text, because your relation could be text, or your just a very expensive label. And then there are some advantages. It's general. You could use for label, text, or a combination of them. It's effective because it has shown to be good for 2-hop, 3-hop questions. And also it's transparent because you can also monitor, like the previous algorithm from the same university, they care about intermediate steps for interpretability issues. And we infer answers by, so this is the relation score. I will explain it here later. So when we go from one entity to another one, there is a, for example, 0.1% chance that we go to another entity, and this goes like a Markov chain. So we also have a score for relation and a score for entities. But we don't. There is no state here. So we have solved it in a different form. So if we start from topic entity, your question, for example, this is the first topic entity, such as Canadian. And then we start from topic entity of the question, and we maintain an entity score vector. I mean, the probability of an entity being activated, because you could use you could use this entity, this topic entity. So each one has a probability. So you attend to some question board. You compute the score for relation. Like any other article that I explained, you could at each step you attend to different words of the question and you compute the score. So like other articles that I have explained. And then you formulate these relation scores into an adjacent matrix. Oh, this is new, because you are saying that, for example, what is the probability that I go from this entity to another entity? What is the probability that I go from ith entity to j's entity? And then now you can multiply the relation score to the entity score, because they are independent. So it's just a simple probability. Probability of staying here times the probability that moving from this entity to another becomes the probability of this. So we can, in this way, we can hop along relations, and we arrive at the target entity, the last entity, target entity, after repeating multiple steps. Then we understand, okay, this is the answer. So the TransferNet, we are embedding the question using this encoder, and using the softmax we have B. QKT is the attention key. So Q is just a linear combination of these hidden vectors. And as I said, the relation score is this, but here AT is entity score, because at each step that you hop, you go to the another entity, you have a score. So we can measure the score. So the entity score, So the current entity score is relation score times the previous entity score. So in order to go to J, you could go from I equal to 1, I equal to 2, I equal to 3, but all of them goes to J. So we are implementing G for label relation. One approach is thus that the paper suggests. It suggests that they have got good results with the summation function. So they use this for G, because it's just a summation of P. And so we have B labels for each entity pair, B labels, for we're going from I to J, because we need a pair in order to describe a relation. And this is the predicate probability for each relation. So we sum all of them. And this is TransferNet because the entity with maximum score is our answer. This is our answer. And so C is just the probability distribution of question hope. Because at each step we have different A1, A2, AT, and then, so our training uses a simple Euclidean distance L2 norm. So this is our loss because we know the answer and because we are just minimizing this. And it is interpretable because we are learning the intermediate scores as well, although we don't need it, but because it is interpretable, we like it. And there are question, attention, relation score, entity score of each step. So it's too expensive. And this is the overall architecture of TransferNet. And this plays an important, this adjacency. If we go from one entity to another, what is the probability that you go from I's entity to J's entity? And you activate what is the entity score, and finally you learn it. And these are the results. You see, I've talked about PoolNet. I've talked today about TransferNet. This is the article. It compares it. GraphNet, and I have explained others as well. But not this one, So another article is subgraph retrieval enhancement. Because our graph is too big, when we have a question, we can just pay attention to parts of it because we don't need all of these billions of entities and billions of relations. We just need to pay attention to what we need. So this is a technique to just create a subgraph of that in this retrieve block. And this is the target probability. What is the probability of answer given this graph? But our subgraph, you sum over subgraph. You may say, oh, subgraph is combinatorially very expensive. How do you do that, Farshad? And we will say, okay, we have a technique. We will reduce it to some finite enumerations of finite. And so we can deal with this issue. No problem for combinatorial perspective. And so we have a prior distribution on subgraph. Like in Bayesian framework, we have a prior. Now we have a prior over the subgraphs because it's a big space. So we try to concentrate on a particular zone. And so we have we want to decouple retrieval, which is this one, retriever, because it just tries to retrieve whatever text we need, whatever information we need, whatever relations we need. And then the answering says, okay, given this question in this graph, what is the probability of the answer? So using subgraphs, there are some pros because a small subgraph is highly likely to exclude answers. So it is bad. So it is bad. It's not pros. But a large one might introduce noises. So this is the pros of that. This is the pros. But this is bad. So because, it is cons. It may exclude the answer because you may miss some answer. And so you see, this is the general architecture. You have retriever and reader. Let's say reader is just a reasoner. And then you have seen different architectures in the past lectures. And so you can use BERT. And so this is the probability of target distribution. What is the probability answer given your graph and question? And we sum over all subgraphs. These are subgraphs. I know you are feeling that this is combinatorial expensive, but you will see that we can do such summation. And then, so we decouple that. This is decoupling. We find parameters theta and phi. Theta is for your subgraph retriever, and phi are the parameters that you should learn for the reasoner. And they are decoupled they are decoupled, we can first train the retriever and then train the reasoner. But you can do it end to end, no problem. And so it's beautiful decoupling because log of, for example, AB is log of A plus log of B. And then you have subgraph retriever. And so the retriever needs to calculate this P theta for any graph. Because it is intractable, because the latent variables is combinatorial in nature, as I said. And so to avoid this enumerating problem of this graph G, we expand top K path. This path, top K path. But they are relevant to our question. So we enumerate all of these paths. And so we induce the subgraph using these paths because we only care about these paths among all paths of the graph that you could imagine. So we are now expanding paths. For example, here we say Turing Award, so it's Wien and graduate. Another entity is Canada, so it's a different path. So path 1 is Wien and graduate. Path 2 could be citizen and graduate. So we enumerate all of them, and then this is their subgraph after merging them. So we are expanding our path, and we need this because we need a threshold for relevance score. This is just a virtual relation. And we use Roberta, like another article from that researcher in Washington University. So F and H is like that, is instantiated by Roberta. So as I said, we have a path we can think about as a sequence of relations. R1, R2, R3. And so it generates these entities, E1, E2, ET. But each of them, this is entity set. Each point, each joint, each node it's like a set. We have a set of entities. And as usual, we need some score. So the relevance of that is measured by this dot product. Because we need the f of q of question and the relation. Question, relation. You see it in all articles. Because we need to know what is the best match for a path of questions. I mean, the words in a question that you attend to. And a path of relations that occurs on the way. And this is the probability of a path given a question. So given a question, what is the probability that I tell you that these are the relationship? And because they are independent, because you have this amount of relations in path P, so you multiply all of these probabilities. Probability of R1 given Q1 times probability of relation 2 given the second word, for example, of the question, and so on. And we have many relations. And finally, this is the general architecture. I explained the retriever. Now let's focus on the reasoner. Reasoner is just using the likelihood that I've just told you. This is just the likelihood, and of course there is end-to-end fine-tuning as opposed to that decoupling, as I said. You can do it end-to-end. And SG here means stop gradient operation. It means that we stop updating these parameters phi, and so our loss, as I said, is just a sum of two loss for reasoner and retriever. We learn them jointly. So So we understand the parameters phi and theta. Theta for the retrieval, phi for the reason.